We're now moving on to inductive proofs. Which is a powerful but simple proof technique. Typically, we'll be interested in proving statements of the form for all k, p of k, and you want to think of k here as being a positive integer, so a natural number, 1, 2, 3, 4, and so on and so forth. And the classic example is p of k is the statement 1 plus 2 plus ... k is equal to k times k plus 1 over 2. So we'd like to prove for all k, p of k is true. One way to go about this would be to first look at p of 1. Okay, is it the case that 1 equals 1 times 1 plus 1 over 2? Yes. How about p of 2? Is it the case that 1 plus 2 equals 2 times 2 plus 1 over 2? Well, this is 3, and 2 times 3 is 6, divided by 2 is 3. This checks out. We could even do p of 3. That's 1 plus 2 plus 3, which is 6. Does that equal 3 times 4 over 2? Yes, it does. But I think you can see that this is not a good proof technique because there are an infinite number of cases. We'd have to check p of 1, p of 2, p of 3, p of 4, and so forth. So what do we do? Well, instead of trying to prove that for all k, p of k is true, we're going to prove the following statement. We're going to prove that for all k, p of k implies p of k plus 1. And then we'll also prove that p of 1 is true. So now if we've shown, let's say that we succeeded in this strategy. We were able to show that p of 1 is true, and we were able to prove that for all k, p of k implied p of k plus 1. Well, then we can conclude from this that for all k, p of k is true. Why is that? Well, if we've proved p of 1, and we've also proved that for all k, p of k implies p of k plus 1, then p of 1 being true implies that p of 2 is true. If p of 2 is true, we can use this statement again that we've proved. P of 2 implies p of 3 is true, so we have p of 3 is true. If p of 3 is true, it means that p of 4 is true, and so on and so forth. Let me repeat myself. If you can prove this statement, for all k, p of k implies p of k plus 1, and you can prove that p of 1 is true, it implies that for all k, p of k is true. And remember, that's initially what we wanted to be able to prove. So we've changed the problem here from proving for all k, p of k to instead showing for all k, p of k implies p of k plus 1, and proving that p of 1 is true. It's sort of a subtle change. We haven't changed our proof strategy too much, but in many, many cases, for various reasons, it's easier to prove this statement and then show p of 1 as opposed to just directly showing this particular statement. We've seen in class that sometimes it's easier to prove something by contradiction or prove the contrapositive than it is to directly prove something. And this is another example of changing your proof strategy. You wanted to prove for all k, p of k. Instead, you proved this and p of 1, and therefore you can conclude that for all k, p of k is true. So now let's use this strategy to actually prove that for all k, this sum does obey this particular identity. So let's prove that for all k, 1 plus 2 plus ... k equals k times k plus 1 over 2 using this proof strategy, which is a proof by induction. So first, we're going to prove the base case, which is a fancy way of saying we're going to prove P of 1. Well, what is P of 1? It's the statement that 1 equals 1 times 2 over 2. And as we said earlier, this is true. So we prove that P of 1 is true. Now we need to prove that P of k implies P of k plus 1. And this is for all k. So remember, how do we prove an implication? We start by assuming that P of k is true. Okay? And we need to conclude P of k plus 1. So what is P of k plus 1? Well, it's the statement that 1 plus 2 plus dot 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 plus k plus 1 equals k plus 1 times k plus 2 over 2. This is the statement that we need to prove. And we get to assume that P of k is true. So think of P of k being true as a fact that was given to you, and we now need to prove that P of k plus 1 is true. Okay, well, I'm going to take this sum, 1 plus 2 plus dot 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 plus k plus 1. Remember, we need to show that this sum is equal to this formula. And I'm just going to look at the first k terms. So I'm just going to rewrite this as 1 plus 2 plus 3 plus k plus 1. I didn't do anything here, I just rewrote it. Now, we know that P of k is true. We've assumed that P of k is true. That means that the sum of these first k terms is equal to k times k plus 1 over 2. Because that is what pk says. It says that the sum of the first k numbers is equal to k times k plus 1 over 2. Okay, so here I applied pk, and I got that this first k terms is k times k plus 1 over 2. This is also called applying the inductive hypothesis. You'll see this in the book. Okay, well, we have one term left. It's plus k plus 1. So I'm going to put them over a common denominator, k times k plus 1 over 2 plus 2 times k plus 1 over 2. And this equals k plus 2 times k plus 1 all over 2. Now notice we proved that the sum of the first k plus 1 integers is equal to k plus 2 times k plus 1 over 2, but this is exactly equal to, this is what we wanted to prove, this is pk plus 1. So we started by assuming pk was true, we ended up proving that pk plus 1 is true, and that completes the inductive proof.